Yeah, so if you ask a person, how does an airplane work? There's 3 or 4 answers.
Okay.
The first answer is really well. Okay. The second answer is, well, it's really simple. I go on the internet, I go to Expedia or Kayak or travel site, and I select a flight, and I buy a ticket, and on the day it's going to leave the plane, I go down and I get on the airplane. That's how it works. Another answer, the third answer would be, well, I go down to the school and I take some lessons, and they show me how to push back on the throttle, and I push up on the throttle, and then I fly the airplane. That's how it works. The fourth answer is, well, you have airlines, and when the airline goes at critical speed, you get a low pressure area above the wing and a low pressure area below the wing because of the velocity of the air over the airfoil, and that creates lift. So you take the airplane and you go to critical. Okay, that's the fourth answer. Now, for using a microscope, atomic force microscope, you can answer that question, how does it work, 4 different ways. And of course, the first answer is really well, okay? But what we find is that for atomic force microscopes, it's better if you have the understanding with the fourth answer. In other words, if you understand what's in it, you'll be a better operator, you'll get better results, and you'll be able to be more proficient with the microscope. Okay, so this is a small presentation here on the microscope instrument, and it kind of shows you how it works. Okay, so this is what we normally do as a 3-day training. We'll just do everything today. So because you already know how to run it, and you're learning because you have access to it. A lot of times what we find is that people have used these microscopes, but at the level of the third answer to the question I just gave, they just kind of know how to push a few buttons. They don't really know how it works. And so what we find is if we can train them how it works, they'll, again, more productive with the microscope. Okay, so to have AFM success, these are the 4 things. The first one is the AFM has to be in an area with minimal vibrations. A lot of people buy these microscopes. They don't realize that it's one of the most sensitive instruments known to mankind. These instruments are capable of measuring vertical displacements on the order of 20 picometers. That's a tenth of a hydrogen atom diameter. It's really small. Okay, so to do those kind of measurements, the AFM has to be in an area with minimal vibrations. This is a good environment. Small air conditioner up there, but very, very quiet. The floor is very stable. When I'm in this room, I can just hear it's quiet. So that's good, but you do have to get on a better table because that table will cause problems. The sample has to be prepared correctly. This is something that is misunderstood with AFM. If it's a clean sample, it's easy. If it's a dirty sample, it's hard. If you're going to look at nanoparticles, they have to be attached to the surface. We'll talk about that. You have to know how to run the instrument correctly. So instruments all have different personalities. So if I ask the question, are people the same or are they different? Well, the answer is they're the same, but they're different. So as humans, we all have 2 ears, 1 nose. Most of us have 2 hands, 2 legs. So we're the same. But we have different personalities. So we're different. And, we behave, say different things. We observe different things because of our personality. AFM is the same way. So if you use AFM Workshop and you go use Asylum, it'll seem different. It's the same thing, but it'll seem different. And so a lot of people that have experience on a Bruker, when they use our microscope, it seems different. Really unusual at first, until they get used to it. So that's because the instrument operation is a little bit different. We call this that, we call feedback or the Z drive, and they have different terminology, things like that. And the fourth thing is image processing skills, and this is something that catches people by surprise. The image that an AFM measures is inherently very boring, and that's because it's actually measuring topography. An optical microscope and an SEM are not measuring topography. They're measuring the derivative of topography. And so therefore, the images inherently are very interesting when they come out of the microscope. So like a SEM measures difference in the emission of electrons. And it just turns out that that's related to topography, but it's not topography. An optical microscope measures changes in refractive index, right? It's not topography. Or changes in reflection from the surface. It's not topography. So when you measure AFM images, you have to process the images, and that requires training and skill. Okay? So we're going to talk about AFM principles, measuring images, and image processing. Image processing, very short. There's a webinar on our website that you can look at to learn how to do this. Okay, AFM principles, we're going to talk about the light lever, piezoelectric ceramics, stage integration. We're going to talk about scanning modes. Okay, so here we go. Any questions? No? So far, no. Okay. This is all so simple. Okay, the first thing you need to understand is what a photodetector is. Okay, a photodetector is some sort of a material that when you shine light on it, it outputs a voltage. In this camera right here, there's an array of photodetectors. That's what a CCD camera, a CMOS camera, that's what it is. It's a material which is sensitive to light. You put a light on it, it outputs a voltage. Shown here, when the light hits the photodetector, the voltage goes up. Okay? Now, I can make a position-sensitive device with two photodetectors. Okay, I have a top one. Can you see this okay? Mm-hmm. The bottom one. See, you're young, I can barely see it. Can you see it okay? Okay, so we have a top detector and a bottom detector. And the laser goes up and down and shines on the top one and the bottom one. And we take the top photodetector and the bottom photodetector and we subtract them with a voltage, with a circuit. So the output of that starts at 1 volt. It goes down to -1 volt. That's when the detector goes from the top to the bottom. Top to bottom, top to bottom. Okay, so you see the voltage? 1 to -1. Well, what's really interesting is at the interface there, the light is a little bit on the top and a little bit on the bottom, and we get a slope. Mm-hmm. Of course, that slope depends on the speed, and it depends on the spot size, depends on the width of the interface. Mm-hmm. But with this, at that interface, I can get a very accurate measure of the position of that laser. Okay? Mm-hmm. So again, top minus bottom. Always remember top minus bottom. Okay? So, using this position-sensitive device, I can measure the deflection of a cantilever, the bending of a cantilever. Okay? If the laser light comes in, goes off a mirror, onto the photodetector, onto the cantilever, onto the photodetector. As that cantilever bends, I can tell how much it bends by looking at this top minus bottom signal. Okay, so in this case here, it starts out at the bottom, it bends up to the top, and then comes back down. But again, at this interface region, it's very sensitive. Okay, so we're going to use this in the microscope, and one of the things is to make sure that that light is right at that interface, because that's where it's most sensitive. Okay? Any questions? No. All right. Now, I can put that laser inside a mechanical structure. We call this a light lever. Some people call it a beam bounce. But basically, we have a laser here, and we have 2 thumb screws. And these 2 thumb screws allow us to move that laser around. So the front thumb screw here moves the laser front and back. The top one moves it up and down. And I can use those 2 thumb screws to get the laser on top of the cantilever. And then I have 2 thumb screws over here on the photodetector. And I can use those 2 thumb screws to get the light in the middle of the photodetector. Okay? So that's called the light lever. And you've seen that in here. You saw me yesterday playing around with that. Of course, you know what this is. All right? Any questions about this? Mm-hmm. Now, when you design the microscope, since you're in mechatronics, what you have to do is you have to get these thumb screws sensitive enough so that you can get the light onto this cantilever. Now, the cantilever is about 35 microns across. And the laser spot's about 20 microns. It's a full width half max. So those thumb screws have to have 100 threads per inch to be able to get the resolution. At 100 threads per inch, you can take that thumb screw and you can just turn it and put it right on the end of the cantilever. Okay? So that's how we design the microscope. All right. So the next subject is piezoceramics. And piezoceramics are electromechanical devices. Again, it's a material. And when you put a voltage across it, it expands and contracts. So you put a voltage across it, it expands. Take it off, it contracts. Now, the interesting thing about these piezoceramics is that they have an expansion coefficient on the order of about 1 angstrom per applied volt. That's inherently the intrinsic value of the material. So what that means is you can go down to the electronics store. It used to be you could go to the Radio Shack, and they may still have Radio Shacks in Mexico. I think they may. I don't know.
They still have.
They've gone in the United States. I have a voltmeter from a Radio Shack in Mexico. That's how I know. So anyway, if it has an expansion coefficient of 1 angstrom per applied volt, and I take a flashlight battery and I put it across there, that ceramic will expand 1.5 angstroms.
Yes. Okay?
Remember, a hydrogen atom is 2 angstroms in diameter. So for the price of a flashlight battery, which is, I don't know how many pesos, not very many, and a piezoceramic, which is like you can buy for $1 or 200 pesos, I guess, 20 pesos, 200 pesos. You can have a mechanical system that can move something. I can move this table, hydrogen atom diameter, for about $1.50. Almost nothing for 30 pesos.
Yeah.
So that's really at the core of these microscopes. Now, these ceramics have to go much larger distances, like 17 microns, say, which is a lot of angstroms. So what we do is they stack them up, and they have different materials, and so they're able to get these ceramics so they'll go maybe 15 microns for 150 volts. Okay, so 15 microns is still not very much. Human hair is about 75 microns in diameter, so 15 microns is about a quarter the hydrogen of a hair diameter. Okay. Keep it all in perspective. Okay, now if you put a voltage ramp on these ceramics, they expand and contract proportionally to first order. Okay. So they expand and they contract. Now, to second order, they don't. And so there's nonlinearities, and we'll talk about that later maybe. But basically, you put a voltage on it, it expands and contracts linearly. Okay? So we can build a scanner, and I showed you this yesterday, what this looks like. And what we do is we have a pivot point here, at the bottom. We have a ceramic here. And it's going to be hard to see, but this here expands, say, 15 microns. And we have a 4-to-1 lever arm here. So if this expands 15 microns, then this goes back and forth 60 microns. Okay? So we have a ceramic in the Y direction here. And then coming out of the page, we have one going in the X direction. So we basically, by pushing here and then pushing in and out of the page, we can move this thing back and forth, this way and this way, 60 microns. All right? Now, this is problematic for mechanical engineers because there's no hinges in here. And there's a little bit of this that's almost like a human body, in that all we're doing is pushing on things and using stresses and strains. There's no bearing surfaces here. So when you show this to mechanical engineers, they go, no, wait a minute, no, you don't want to do this. We're just pushing on things. To some degree, it's like how your body works. We have muscles and things in here, and we just kind of pull on them. And, it's not like we have a door hinge. Okay? So anyway, so then we can put a Z ceramic here to move the sample. The sample's up here at the top. So now we can go up and down. So we can go X, Y, and Z. Okay? It's a very simple device. And so one of the things we talk about this company and how we sell these microscopes at these affordable prices I use that term loosely. We sell our scanners here for $4,000. That's because we figured out how to make them using this very simple technique. And you saw yesterday I repaired a scanner. We took the ceramic out, I put a new one in, it took us about 10 minutes, okay? If you buy a microscope from the other companies, those scanners cost $20,000 to $30,000. Okay?
Mm-hmm.
That's as much as our microscope, right? And if a student breaks it, it's like, you know. And so that one of the things about our particular company is that if a student breaks it, it's not the end of the world. I mean, we repair these scanners, we charge $1,000. That's what it would cost. It's not. And a lot of times you can repair it yourself because you can just buy the ceramic and put it in yourself if you want. Okay? So that's the scanner. You guys saw one yesterday, and we have a ceramic. There's a ceramic in one of these bags here. These right here. You can see that this is the ceramic, and that's the end cap. You see the end caps here. They're black, broke off. Let me check this because it could be important. It could be Joe Biden. So that's the ceramic. Now you notice on that ceramic that there's strain gauges on either side, and those strain gauges are used to correct the second order nonlinearities. Okay, so to first order it's linear, but the second order is nonlinear, and so we put strain gauges on there, and we use those strain gauges to linearize the motion. Okay. You can see the strain. There's a pair of temperature compensated strain gauges on there, and we use a Wheatstone bridge to linearize. You know what a Wheatstone bridge is?
Wheatstone bridge.
Okay. It's a.
I saw that in some moment in my life.
Yeah.
hard to understand. Yes, it has some resistances like this and this.
Yeah.
The Wheatstone.
Yeah. And so the circuit board, a little circuit board here on the microscope. Since you're into mechatronics, and there was one out here yesterday, there's one here somewhere. This circuit board has 4 Wheatstone bridges on it, 3 Wheatstone bridges. Okay. And each of one is X, Y, and Z, and that's for those strain gauges. And it's used to measure those, and we use that to correct the motion of the ceramics. Okay? All right. So now we put this light lever AFM, it's a force sensor, on a Z drive. Okay, and that's a stepper motor on a linear translator, and it drives this whole thing up and down. Okay, and you saw that yesterday. It goes, and you see me. I come in the back, and I'll turn that thing to move it up and down by hand. Okay, but you can do it electronically, of course. And so if we put the scanner inside there and we drive that needle down, we see the cantilever bends. That's not a surprise, right? Okay. See there, it bends right there, and that causes the light to go across the cantilever. Okay. So now I can look at the voltage output, and I can see that when I hit the surface, the top minus bottom signal changes, and the electronic signal changes. Right? Now, here's the hard part. Okay, you guys ready? This is the hard part. This is the hard part to understand. Okay. Now, you're trained as a scientist.
Yes.
But you're trained as an engineer.
Yes.
Okay. It's an interesting thing. In an engineering class, on the first day, you'll be trained about feedback control. But a scientist almost never gets training in feedback control. No. It's the weirdest thing. So anyway, what we're going to do is we're going to take the output of that top minus bottom signal, we're going to feed it back into the Z ceramic. So that when the cantilever bends up, the ceramic will pull back. And you'll see what happens here is that the cantilever bends a certain amount, and then after it bends that amount, the Z ceramic goes down. Okay, so that's called the Z feedback. Basically, what it does is it takes the top minus bottom signal and feeds it back into the Z ceramic. So when the cantilever starts to bend, At a certain point, the feedback is activated and it goes down. Okay? All right, so feedback control.
Yes.
You got that?
Yes.
All right, we're almost ready to scan a sample. So here we go. Okay, so now we're going to turn on this voltage ramp on the Y ceramic. And we have this feedback loop turned on. And you see what's going on there is the cantilever stays bent the same amount. And as we scan back and forth, this Z ceramic goes up and down. Okay? So what's going on here is that the voltage on the Z ceramic is the image of the surface. Okay?
Okay.
Do you understand that?
Yes, I don't know how to explain that, but the movement of the sample with the cantilever is proportional for the voltage.
Yeah.
With that, we do need the image
Right.
of the surface.
Right, that's exactly right. Now, yesterday you asked me what the error signal was, the right-hand side image that we had up there, the error signal. So what happens is, if the feedback loop can't keep up, the probe hits the edge of the surface, hits the edge there and it bends. Okay? So that's the error signal. It's the difference between the set point and the measured value. Okay? Now, the way I describe that is this, and I'm not going to do it for Mexico, I'm going to do it for the United States. So Chicago is in the middle of the United States. San Diego's down here, okay? And if I take an F-16 fighter jet, which will go Mach 2, 1,000 miles an hour, and I tell a pilot, I want you to fly from Chicago to San Diego at 2,000 feet above the surface of the earth. The guy gets in the airplane, he takes off, he's flying along, he's going over Nebraska, he gets to Colorado. It's like, pull back, pull back, pull back, because there's the Rocky Mountains. Okay? Now, we told him 2,000 feet above the surface of the earth. The mountains are 14,000 feet high. Pull back, pull back. Well, guess what? He can't pull back fast enough. Hits the side of the mountain. That's the error signal. Okay? Now, he has a choice. If he were to fly at 100 miles an hour, go more slowly, he could pull back. It's my son. He knows I'm in Mexico. He thinks I'm surfing. Okay? Okay? If you don't want to hit the surface, if you don't want to hit those high mountains, you can slow down. So in the microscope, you can slow down the scan rate, and you go over big features, okay? And you won't break the probe. Okay? Do you understand?
Yes.
Okay. Now, in the microscope, there's many different modes of operation. And there's two topography modes. There's what's called non-vibrating mode, or some people call it contact mode. And then there's another one called vibrating mode, which can be called tapping mode, intermittent contact mode, non-contact mode, near contact mode, okay? We're going to talk about the two topography modes, and then there's 1,000 other modes. There's MFM, magnetic force microscopy, phase mode, lateral force microscopy mode. There's many, many, many kinds of modes. But for today, we're going to talk about the topography modes, okay? Non-vibrating and vibrating mode, okay? So one of the things that you have to remember is that every sample in ambient air has contamination on it. Now, there is no such thing as a atomically clean surface in ambient air, okay? Because in ambient air, you have air molecules. You have, inside those air molecules are contaminants, a lot of water, condensation, things like that. It gets on the surface. And so when you take a needle and you push it down towards the surface in ambient air, the contamination layer wets the probe, and capillary forces pull it down. Now, in a lot of literature for these microscopes, they talk about van der Waals forces. Now, And if you want to see van der Waals forces, go in ultra high vacuum, 10 minus 10, 10 minus 11 torr, clean the surface to atomic cleanliness, and you'll see the van der Waals forces. They extend out from the surface maybe 5 angstroms, maybe 7 angstroms. In atomic force microscopes operating in ambient air, you see interaction forces as much as 50 microns from the surface. Okay, maybe 50 nanometers, excuse me, sometimes 10 nanometers. A really clean surface, it might be 5 nanometers from the surface, but that's the contamination on the surface, okay? And so when you bring the needle down, that force will dominate the interaction between the tip and the surface. So when you do force distance curve in ambient air, a lot of times you'll see the needle be pulled in before it touches the surface, okay? So that's shown right here. In ambient air, when the surface comes up to the needle gets pulled in. It's called the attractive regime and then pushed away, okay? And that can occur sometimes, 10, 20 nanometers from the surface. It's called the attractive regime, okay? And if you use a cantilever with a really low force constant, it'll get pulled in like this, right? But a really stiff cantilever, it'll get pulled in a little bit, okay? This surprises a lot of people. I don't know why, but there's a lot of misinformation out there about this in the scientific literature. So when you scan over a surface in contact mode, the cantilever stays bent the same amount, the needle's pushed down through this contamination layer, and you just scan back and forth. Now, one of the things in AFM, if you operate it in air, sometimes you can scan a small area and zoom out, and you'll see that the needle's pushed material off to the edges, okay? In fact, you can take a sample that's been scanned with contact mode and put it in SEM, and you can see the square where the AFM scanned. Have you ever seen this?
Yes.
Yeah.
Yes.
A lot of people don't know what's going on. Like, what's going on? Well, that's lithography. The needle's pushing things around, So I put the lithography software on your.
So you're sweeping the floor.
You're sweeping the floor, yeah. In fact, you can come back and you can see the scan lines. If you zoom in, sometimes you can see the scan lines from where the needle's pushed in the contamination layer. Yeah, so that's important to remember. Okay. Any questions? All right, are you ready for the next slide? Here we go. Okay, so the next one's called vibrating mode. In vibrating mode, which is called tapping mode, intermittent contact mode, near contact mode, non-contact mode, true non-contact mode, okay? So what happened was, during the 1990s, the vendors decided they were going to try to confuse the customers. And they were going to sell them something new, okay? Oh, we're going to sell you this new thing, tapping mode, okay? And what it was it's all the same stuff, basically. It's just a vibrating cantilever, and you can change the vibration amplitude, the vibration frequency, or the amount of reduction of vibration amplitude when you interact with the surface. It can be this much, or this much, or this much, okay? And that gave rise to all of these, quote, modes, but it's basically all the same stuff. What you do is you put a little piezo underneath the cantilever, and you cause it to vibrate. Now, if you take a cantilever, you can vibrate it below resonance. If you vibrate below resonance, the end of the cantilever will follow the stem of the cantilever. Okay, at resonance, you'll get absorption of energy, and you'll get a larger motion of the end of the cantilever. That's at resonance. And then above resonance, it goes the opposite. It's 180 degrees out of phase. Okay, and so we'll do a resonance curve here with your cantilever. We get down here, and you'll see that. So we can take this cantilever, we can vibrate it. Now, the cyclic piezo is. These are probe holders. Some of these are probe holders. Yeah, I don't like to take this out. I'm pretty close to the surface, so I don't want to take that out. No, those are samples. Those are mine.
What are you looking for?
A probe holder.
The probe
Oh, here's one right here. There's a probe holder. Okay, and you can see on the probe holder where the probe is, and you can see underneath it, you see 2 wires.
Mm-hmm.
Underneath there, that's the tickler piezo. That's a little piece of ceramic,
Mm-hmm.
right? And that's what causes the
vibration.
yeah.
Oh,
Este piecito blanco.
este.
Mm-hmm. Yes.
Little wires coming to it.
Okay, yes.
Okay, and actually the signals for those 2 wires come in here and here.
Mm-hmm.
On the light level, you can see those on the light level when you look into it.
Mm-hmm.
Sometimes those things need to be cleaned or. Okay, so that's called vibrating mode. Okay, so what happens is we put this in the microscope, and if the cantilever goes up and down, the light goes across the photodetector, and you get the vibrating output. Okay, and then you can feed that into an amplitude detector.
Mm-hmm.
And an amplitude detector measures the amplitude. Now, if you bring a vibrating probe down to a surface, okay, it's vibrating, bring it down to a surface, as it begins to interact with the surface, the vibration amplitude is dampened, okay? And if you compare the drive signal to the output of the photodetector with an amplitude demodulator, you'll see that as the needle goes into the surface, it's closer and closer, the vibration amplitude will go down. Okay, and that's shown right here. See the red dots? It's kind of, see the cantilever's amplitude. This is no surprise, right?
Mm-hmm.
Okay. So in vibrating mode, what you do is you scan over the surface, and needle can come in and out of the contamination. Okay. But you keep the vibration amplitude the same. So the feedback loop is activated to keep that vibration amplitude the same.
Mm-hmm.
So when you scan in vibrating mode, the cantilever vibration amplitude stays the same.
Yes.
Okay?
Mm-hmm.
And you don't push the material around. Now, you notice here that in this case right here, the vibration, the tip is coming in and out of the contamination layer. You get a very, very, very slow vibration amplitude here, and the needle will just stay inside the contamination layer.
Mm-hmm.
That's where the highest resolution imaging is done. It's difficult to do. You have to really reduce the vibration amplitude to a very small amount, and then go inside the contamination layer. And the problem is that the needle can jump on top of the contamination layer and go back in, right?
Mm-hmm.
So most people just have this big, huge vibration amplitude. The problem is it kind of breaks the probes eventually, wears them down.
Mm-hmm.
Okay. All right. Any questions?
Mm-hmm.
No. All right.
Probablemente se ha confundido porque no tengo preguntas, pero ya trabajamos en el libro, entonces.
Uh-huh. Yeah, he wrote a review about AFM.
Okay.
So he, at least
Basic
he wrote
ideas. Yeah.
he wrote
Okay. Good.
about
Oh,
it.
this is a good refresher. Okay. Good. Yeah. Okay. So for AFM operation, you have sample preparation, probe approach,
Mm-hmm.
line scanning, you zoom in, and then you have to process the image. Okay? So, sample preparation, the sample has to be clean. A lot of students don't understand that if you have a fingerprint on the sample, it's not clean. Fingerprint's about 50 microns thick, right? Okay? So that's a no-no, okay? We see a lot of times where students are trying to scan samples and they're filthy dirty. They have a reference sample that's 10 years old. Like the reference sample you gave me yesterday was pretty dirty.
Yes.
Not just particles, but it had a lot of surface contamination on it. And the reason I know that was when I came down to the surface, okay, if a needle comes down to a clean surface, it goes,
Uh-huh.
okay, it just goes, on a dirty surface, it goes, it's kind of like a drunk sailor. It comes in, okay, very slowly, it's kind of, okay. Materials must be attached to the surface. And so, again, if you're looking at DNA or cells or nanoparticles or anything that you put on a surface, you have to make sure that it's attached to the surface. Otherwise, the needle can just push it around. A lot of people spend months and months and months trying to see stuff and they never see it because they push it around.
Mm-hmm.
Okay. You have to have a conductive path between the probe and the surface. We're going to work on that today on your microscope. Okay, and the sample has to be rigidly mounted in the microscope. A lot of times students get lazy and they'll just stick the thing in there without attaching it down, and I had a customer the other day, they were looking at a sample. It it was a nanoelectronics. It was a line and had these like wiggle marks over. I said you didn't put you'd have to make sure the sample's rigidly mounted. They just put the sample and they didn't tape it down. Right?
Mm-hmm.
So anyway, those are the primary things. Now the next one is called the tip approach. Now to get the probe to the sample, suppose it's a millimeter away and you want to get to the sample in a minute. Okay, that's equivalent to flying to the moon and stopping in a minute. Okay? Now, what do you think would happen if you had a spaceship and you sent it to the moon, you tried to stop it within a minute? It would overshoot. And it would hit the surface and it would kill the people in the boom. Yeah, so we have this thing called the woodpecker tip approach. Woodpecker tip approach. Okay? So you have two things. You have a Z motor. It can go down and down and down and down and up and up and up and up. You have a ceramic, which can go up and down. Okay?
Mm-hmm.
Now your Z ceramic goes up and down 17 microns.
Mm-hmm.
So what we do is we take the Z motor and we step the needle down. We go up, so we do see it. No, we step it down again, do it again. And we keep doing that. We bring it down till eventually we see the surface. Okay, then we're in feedback. Okay, so this is what that looks like. This is a video looking straight in on the side. This is the probe. This is the sample.
Uh-huh.
And you hear the microscope go click, 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 click when you're doing this.
Yeah, so each step it approaches more and more.
Yeah.
Mm-hmm.
All I can think about is carnitas. We're not carnitas for lunch, right?
Yeah, yes, sure.
Just checking.
Yeah.
That's what I think when I look at that. I'm like, oh, carnitas for lunch. Okay. See the cantilever?
Yeah, and it's bent.
Bent a little bit?
Yes.
Isn't that cool?
Yeah, it's very cool.
That was done, somebody took this optical microscope and shone it in from the side.
Yeah, I have a patient student to do that.
Yeah, you have to get it just right.
Yeah.
Yeah. But anyway, so that's what it looks like. Okay, you got it?
Yes.
Now, when you first use the microscope, you typically break the tips when you use tip approach. But usually you're looking at fairly large things. Now, one of the things with an AFM, when I talk about large things, I'm talking about 10 nanometers, okay? Which by anyone else's standards is really small. When I talk about small, I mean less than a nanometer, okay? So when you start to scan image things that are less than a nanometer, to be very careful about tip approach.
Mm-hmm.
Okay, so now you scan back and forth, you have to optimize the GPID parameters.
Mm-hmm.
Now, yesterday we were looking at those, that standard you have. Those things were 200 nanometers high, okay? We would have to scan really slowly not to have any error signal, okay, on something that large.
Mm-hmm.
Our reference samples have heights of about 100 nanometers. If you scan it half a hertz, you're still going to see the error signal go up and down, but if you scan it a tenth of a hertz, you'll see a very, very small error signal, okay? Now, this is for the engineers in the crowd. This is the Z feedback control. So we have a top minus bottom signal.
Mm-hmm.
And we have a set point. Okay. Goes into a differential amplifier. We compare those two. Okay. This is like in the oven when you want to cook a frozen pizza. You put the thermostat to 400 degrees. And there's a thermometer in the oven.
Mm-hmm.
And if this is 400 degrees and this is room temperature, this error signal here, it turns on the heater. But in a microscope, we have a cantilever with a top minus bottom signal and a set point. And then we compare those, we get an error signal. We put that through a PID controller. Do you know what PID controller is?
Yes.
Okay, proportional integral derivative. And then we use that to control the ZPA zone. Okay?
Mm-hmm.
So in the software, you see these we call them GPID parameters. It's G times PID.
Okay.
G is a multiplier. It's a vector. Okay? So if the top minus bottom signal here is, say, we always set this between 0.5 and 1 volt.
Mm-hmm.
Okay? For reasons which I'm not going to explain.
Okay.
Okay? If we want to have the cantilever bend 0.2 volts, we would put this at 1.2.
Okay.
All right?
Mm-hmm.
If this is 1 volt and this set point's 0.8 volts, it ain't gonna work. You'll never see the surface, right? Now the software's set up so that what happens is when you go to a chip approach, it takes this value and adds a value to it, okay, for the set point, okay? So when you optimize the PID parameters, what that means is you want the cantilever bent the same amount below a feature as above a feature. So it's just scan over the surface, right?
The same.
And you can see that if PID parameters on are optimized, when you have it say straight here, when you go over a feature, it'll bend. Okay?
Mm-hmm.
This is the only thing that differentiates an AFM from a profiler, from a stylus profiler.
Mm-hmm.
In an AFM, it's a constant force as you go across the surface. In a profiler, it varies.
How come you didn't do that?
Huh?
I thought the profiler applied a constant force also.
No, it's variable force.
Okay.
Yeah. Okay? Now, if you take a look at the optimizing the set point, I'm going to say something. This is the only thing you have to remember from this presentation. If you're in contact mode or non-vibrating mode, to increase the tip sample interaction, you increase the set point. That causes the cantilever to bend more.
Mm-hmm.
Okay? If you're in vibrating mode, you reduce the set point. That causes the vibration amplitude to reduce. Okay?
You are more time onto the surface.
Right. You're increasing the tip sample, the vibration amplitude is going down. Okay? So what happens to most students is they go in to start scanning and they'll see something what's called false feedback. And the image looks like, I'm dreaming, I'm dreaming, okay? And if they're in vibrating mode, you say, okay, reduce the set point 10%. And all of a sudden, the image becomes perfectly clear. Because what's happened is the needle is pushed down through the contamination layer, okay? This happens to every single AFM operator. And when it happens, they go, what is going on here? This is terrible. I say, if you're in contact mode or non-vibrating mode, you increase the set point maybe 10%, and all of a sudden, boom, just beautiful image. And it's really astounding because it happens to every single AFM operator. And once they've done it a few times and they remember this, it's like, oh, okay, I want to, the image just looks all kind of fuzzy and blurry, kind of, like I'm too much tequila. Not that you guys drink tequila. I do.
It's kind of.
So, do you have sangria here? Sangria? No sangria?
Yes. Well, you can get something. But...
They don't sell that in the United States.
No.
Okay. So if you take a look at the Z feedback loop, there's about 5 different images you can get out of the feedback loop, and they're shown here. Okay. You can do the Z drive, which is the voltage that goes to the Z ceramic. Okay. You can take the error signal. So usually I put this one on the left image and this one on the right image. Okay. Mm-hmm. But you can also take out the phase image if you're in vibrating mode, and that's a measure of the hardness of the surface. It's good for polymer samples.
Mm-hmm.
You can take out the left minus right signal in contact mode or in non-vibrating mode.
Mm-hmm.
You can look at this output of the strain gauge that's called Z sensor. Okay. You can display any of those images on your computer screen. All right. Any questions about this?
No.
So when you scan an image, you can zoom into a smaller area. So you use a big area, 50 microns, 20 microns, 10 microns. Yeah. So now, one of the things about the AFM is you have to realize that the probe is got to be taken into consideration, the probe geometry to what you want to image. Now, one of the questions people ask all the time is, what's the resolution of your microscope? Okay. Now, if you take an optical microscope or an electron microscope, the resolution is very easily defined as the minimum differentiation you can see between 2 points. But in AFM, there really is no definition for resolution. I have a write-up about this on our website because the resolution that's vertical dimension can be 20 picometers. That's this dimension. But if the diameter of the probe is a micron, the resolution in this direction is a micron.
Mhm.
Okay, so what's the resolution? A micron. So it depends on what you want to look at. And so we get this a lot from people that are very, very new to the field. So what's the resolution of the microscope? And the problem is this, and we talked about this yesterday. So I'm a scientist, trained as a scientist, but I did end up doing business. And I actually managed a sales force of 100 salespeople for about 3 or 4 years, 5 years, okay? And one of the problems is when you have a scientist doing sales, and you have to, if a scientist wants to go into sales, which can be very lucrative, you have to train them how to answer questions.
Yeah.
So if somebody asks me, you guys have Coca-Cola here, right? Is a Coke can round? Well, most people would just say, yeah, Coke can's round. Scientists would say, well, what do you mean by round? How round? I mean, it's not perfectly round. Besides that, if you go around this way, it's round, but if you go around this way, it's rectangular. So, could you be more specific in your question?
Yeah.
Okay. And so what I found that was when I'm selling, when I'm a salesman, because I can be a salesman, if somebody says, what's the resolution of your microscope? I have to give them a sample answer. I say 20 picometers. Right? Because if my competitor says 20 picometers and I say, well, that really depends. Because if you want to look at the XY resolution or the vertical resolution, it goes right over their head. Guess who's going to win the sale? So anyway, but scientist to scientist, scientist engineer. An AFM resolution you really have to really decide what it is you want to measure to figure out if it's going to have the right resolution. And it depends on the probe geometry, of course, because in this case here, I can see the bottom of the hole. But in this case here, I can't see the bottom of the hole, but I can still see the features there. So I can resolve that feature. I just can't resolve the bottom of it. Okay.
Mhm.
So, all right. Okay, so the same with when you're looking at nanoparticles, you have to look at the probe geometry. So if you're looking at nanoparticles that are 1 nanometer in diameter, probe geometry is very important. But if you're looking at nanoparticles that are 50 nanometers in diameter, which are huge by AFM standards, then the probe diameter doesn't matter. Okay, so it really depends on what you're looking at. There's a lot of different kinds of probes and cantilevers. We use these cantilevers that are made with silicon micromachining, MEMS technology. So and they kind of look like this. But there's all kinds of probes. There's a lot of different companies that sell these things. We buy them from another company. Okay, so image processing is important, as I said before. These are the primary things is process the image, display the image, and analyze the data. Now, when you process the image comes into the computer is the 3-dimensional array of numbers, X, Y, and Z. You got 3 numbers, X, Y, and Z, topography image, okay? Now, if you take those numbers and you change them, you've processed them. For example, if the image is not level, you do a background subtraction, okay? You've changed those numbers. They're not the same. It's not the same numbers. You potentially introduced error into the measurement, okay? When you change display, you don't change those numbers. You just change how they're visualized. In other words, they're the same numbers. It's just you have a different mapping or representation. So in other words, I can say if I have 16 color scales, I can say color number 15 is red, or I could say color number 16 is green, okay? And then analyze it is extracting data from the matrix, line profile, fractal analysis, particle analysis, a number of different things you can do. Okay, so the simplest leveling is the simplest process is leveling. And so this is a test pattern. It's high here and low here. So what I do is I subtract that. background. And usually when you bring an image into the computer, first thing you do is a leveling process. Okay, so we do leveling. This is a case of display. So this image here is the same here. This is in Christmas colors.
Mm-hmm.
This is boring scientist colors. So same data, just we changed the representation. Now we've made a 3D light shaded view.
Mm-hmm.
Same data, we just changed how you visualize it. The numbers are all the same. And this is the simplest data processing. It's just a line profile to extract that. We do surface texture, SA, engineering parameters for noise floor, things like that. So anyway, but there's a number of different analysis. We use Gwydion software.
Mm-hmm.
All right, so AFM success, AFM in the area of minimal vibrations. Like I say, this is a good space, your table stinks. Sample prepared correctly. I hate to see these AFM sitting on a crappy table because I know it's not going to give the best performance. Sample prepared correctly. Knowledge of the instrument parameters and image processing skills. Okay, do those 4 things, do anything you want. Using an AFM takes about as much time to learn as driving a car. So think of it that way. If you don't take the time to learn, you won't be very successful. Okay? Any questions?
Nunca me va a perdonar lo de la mesa, pero...
Yeah, well,
No questions.
but no, everything fine.
Okay?
Okay, thank you very much. Muchas gracias. Esta fue la presentación del doctor Paul West de la compañía AFM Workshop, que vino a hacer el entrenamiento en el manejo del equipo y el mantenimiento general del equipo que tenía que hacerse al instrumento. Gracias.